Hello, this video is an introduction to exponential functions. Exponential functions are functions in the form y equals a times b to the power of x, where b has to be greater than 0. So an example of one equation could be f of x is equal to 2 times 3 to the power of x. So in that example, a is 2 and b is 3. We meet the requirements because b is greater than 0. The first thing we have to know how to do is how to evaluate exponential functions. What that means is they're going to give us a value or a number for x, and we're going to plug that in and then simplify. So in this example, they are saying to, let's see here, plug in 2 for x, so we'll go ahead and do that. So we'd have f of 2 is equal to 2 times 3 to the power of 2. So they're saying x is 2, tell me what y is, or my output. Here, if I'm following my order of operations, I would do 3 squared first, which would give me 9. So now I really am left with 2 times 9. So f of 2 is equal to 18. Remember, that's another thing, or the f of 2 could also be written as y, but essentially that says when x is 2, y is 18. We can do the same thing for finding f of 5. That means you're going to make x equal to 5. So I would simplify the 3 to the 5th power first, this little chunk. You could use a calculator if you need to. So 3 to the 5th power gives me 243. And then I would have to multiply by 2. So f of 5 is equal to 486. So that's our first skill, being able to recognize those equations and then evaluate them, which means plug something in. Okay, our second slide talks about how to identify them as well using a table. Exponential functions, you guys, their key characteristic is you are always multiplying by a constant. So like in our first example, our b value was 3 on that first slide. That's what we were multiplying by each time, 3. So really what we need to do here is check our y values. So we go from one to the other, and we want to see if we are multiplying by a constant. We don't care about adding or subtracting, only multiplying. So to get from 2 to 4 would be times 2, 4 to 8 times 2, and to get from 8 to 16 also times 2. So here all of these values are the same. That means yes, it is exponential. And if I were to write an equation, if we remember y is equal to a times b to the x, well here b is 2 because that's what I'm multiplying by each time. Now a is my starting value when x is 0. So here is where x is 0. That means my a value is 2 because that's what y is when x is 0. So my equation would be y is equal to 2 times 2 to the power of x. Let's check out our bottom one. So 270 times 90, I'm getting smaller. If you remember with exponential functions, all we care about is multiplication. So if I want to go from 270 to 90, I can multiply by a third, and that will work. To get from 90 to 30, I multiply by 1/3. And 30 to 10 is also 1/3. So it is okay if it's a fraction as long as it's positive. So here, again, it's yes. If I wanted to write an equation for this example, b is a third. Remember, a is our starting value, which is here. When x is 0, y is 270. So my equation would be y is equal to 270 times 1/3 to the power of x. Again, it didn't ask for an equation, but I wanted you guys to see what those could look like if you were to write them yourself. Okay, next thing is deciding if something's an exponential function from ordered pairs. This is very, very similar to a table, just that they are written a little bit differently. So remember, ordered pairs, x comes first, y is second. So I'm just looking for my y. So I'd go 1.5 to 3, well that's times 2. 3 to 6 is times 2. And 6 to 12 is also times 2. So this would also be a yes because I'm multiplying by 2. Okay. In this case, if I was going to write an equation, there's my starting value. So a would be 3, b would be 2. My equation would be y is equal to 3 times 2 to the power of x. Let's look at our second example. Negative 9 to 9. Well, I'd have to multiply by negative 1. 9 to 27 is times 3. Well, already we have two issues. These two are not the same. And also b, which is what we multiply by in our equation, has to be greater than 0, which means it's positive. This is negative, so that will not work. This is a no. It is not exponential. Okay, moving on to a word problem example. It says the function f of x is equal to 1500 times 0.995 to the power of x, where x is the time in years. Okay, so we know x is all about years. That models a prairie dog population. How many prairie dogs will there be in 8 years? Okay, so essentially it's telling us that our time, or our x, is equal to 8, because it's saying it's after 8 years. And they want us to figure out how many prairie dogs there will be. So we're going to plug in 8 for x. So I'll have 1500 times 0.995 to the power of 8. This is one you're going to want a calculator on, and what I would do is do the 0.995 to the power of 8 first in my calculator, and then next I would multiply by 1500. So I would get f of 8 is equal to 1441.04. In this case, if we're talking about prairie dogs, I would just round to whole numbers. So I would do 1441 prairie dogs as my final answer. Okay. Our last part is graphing exponential functions. You'll notice in my 2 examples, I generally start my tables at -1 and I go up to 3. That's going to give you a pretty good idea of what your graph will look like when you're trying to make it. And then you're going to go ahead and plug all of your different x values in. I'm going to show you 2 different ways to do this. So I'll show you one example on this problem and the other strategy on the second example. Okay, so first thing is let's just plug the different x values in. So first x value is -1. So I would have 3 times 4 to the -1. Again, you can do this in the calculator. So you do 4 to the -1 and then multiply by 3. The other thing is when you have a negative exponent, so like here it's 4 to the -1, that means it's going to become 1 over 4 to the power of 1 when we studied exponents. So essentially it's 3 times a fourth, which would be 3/4. I'm going to write it as a decimal, 0.75. And I would keep repeating that. So next I would plug in 0. So I would have 3 times 4 to the power of 0. Keeping in mind I'm just substituting in for the x there. Anything to the power of 0 is 1. So I essentially have 3 times 1, which is 3. Keep going with this process. 3 times 4 to the power of 1 is 3 times 4, which is 12. If you keep going, I next got 48 and 192. Okay, you can notice with these that your numbers are going to go up really quickly. So you can see they get really big or really small very fast. That is a characteristic of quadratics. All I have to do from here is graph. If I were going to graph this, what I would probably do is actually go up by tens on my y-axis to make it a little bit easier. So, for example, this would be 20, and then 40, and then 60 instead. And now I can go ahead and graph. So the 0, 3 is going to be hard for me to get right on here. Hopefully on your paper it's a little bit easier. I have to be somewhere right around there. Sorry for my squiggles. Let's see if I can make this a little bit nicer. 1 would be 12. Not very dead on, but you get the idea. 2 would be 48. And then 3, 192 is not going to fit, but I know it's going to be somewhere through my points there. So again, hopefully on your graph paper you can get those points drawn in a little bit nicer. Okay, last example. I'm going to show you a different strategy for figuring out your y values here. In your table, if you start where x is 0, well, we know when x is 0, that's our a value, right? So if I did -5 times 2 to the power of 0, that becomes 1. So I really just have -5 times 1. This is -5, which is my a value. Then 2 is what I'm multiplying by each time. So essentially I can take my -5 and just multiply this times 2, because that's my b value. So that means if I plug in 1, I should get -10. If I multiply -10 by 2, I'd get -20. Multiply by negative 2, I get negative 40. So as I go down, I should be multiplying by 2 each time because that's my b value. Now if I want to go the other direction in my table, so I'm essentially going backwards, I would have to divide by 2. That would mean that this was negative 2.5 to start. So that's another way to think about this as you are making your tables. This one, if I were to finish putting it on my graph, I'd probably go up by 5s. How about on our y-axis? So this would be negative 10, negative 20, negative 30. Again, I'm sorry, it's not super clear on the iPad, so I'm drawing them in. But 0 would be negative 5, 1 would be negative 10, 2 would be negative 20, 3 would be negative 40. We're a little bit off, and then that negative 1 was negative 2.5. Just trying to eyeball it the best we can. And then I'll go ahead and draw my curve through it. And you guys will notice with these exponential functions, this arrow here should be drawn nicer because really what it should do is approach that x-axis, but it's not crossing it because these values will keep getting closer to 0, but they're never going to cross it. So you'll notice, like we did in our previous example, that the graph will get really, really close to y being 0, but we'll never actually touch that. Okay, your note sheet should be filled in. And from here, if you still have time, go ahead and work on those practice problems on the worksheet. Let me know if you have any questions. Thank you.